So, as I said, we're fortunate enough to have Michael and Saeed talk us through their engineering experiences at S&C Electric Company. S&C is a leading provider of switching, protection, and control solutions for electric power systems, keeping the lights on for homes and businesses globally. They have over 100 years of experience globally and over 60 years of experience in the Asia-Pacific region. Michael Higginson is a manager of engineering services at S&C with over 9 years of experience in the electric power industry. He has led power system consulting and analysis for distribution systems and microgrid development. He has focused on distributed resource integration, power system protection, and automation. He has led power system analysis and relaying efforts for award-winning microgrid systems and renewable generation projects. He has authored several papers on microgrid design, operation, and smart inverter system impacts on power systems. Michael is a recipient of several industry awards and has been awarded 2 patents by the US Patent and Trademark Office. The second presenter we have today is Saeed Kamalinia, who is a senior manager in the Power Systems Solution Division of S&C with over 15 years of experience in the electric power industry. He is the author or co-author of more than 30 journal papers and conference articles in various areas in power systems, including renewable generation, distributed generation sources, and power system operation. His articles have been cited for more than 600 times by other researchers and professionals. Saeed is a recipient of several industry awards and holds PhD in electrical engineering from Illinois Institute of Technology. With that introduction, gents, we're really looking forward to your presentation today, and I really appreciate you taking valuable time out of your schedule. I will stop sharing my screen now and I hand over to you, Saeed.
Thank you, Ash. Okay, as I'm taking over, let me actually take care of the logistic here first, make sure I'm doing it right. So you should be seeing the front page of the presentation.
Yep.
Okay. Yeah, let's just move on. Good morning, good afternoon, good evening, depending on where you are. I'm coming to you just past 6 p.m. Central Time in United States from Chicago. I wanted to first, of course, thanks Sigray Australia NGN for the opportunity and all of you to take time attending this webinar today. I've been myself involved with Sigray US NGN for several years. It's my favorite industry group, affinity group. So I really I'm excited to be here and be able to continue my contribution to Sigray. With that, Ash, thanks for introductions, but I'll pass right into the content. Today, I plan to talk about how utilities integrating distributed energy resources and microgrid into their modernization plans. We then go over some key analysis considerations that need to be made as part of the integration of such resources into the system. The bulk of today's presentation will be focusing on 3 areas that introduce most of the challenges for integration of DERs and microgrids, including protection, control, and dynamic stability. We finally conclude with some key takeaways and possible future works. DERs have become an integral part of the grid modernization for many utilities around the world. What you see in this picture is a beautiful aerial view of the University of Illinois at Urbana-Champaign campus, which hosts a microgrid developed by our engineering team just about who has adopted the microgrids to improve the quality of the service to their customers. The microgrid can be recognized on just the bottom left corner of your screen with the interconnection substation next to the PV panel and wind turbine. The microgrid also includes battery energy storage and natural gas generator. If I may kindly request all the participants just take a moment here and make sure that your audio is on mute. Yeah, just a little background noise here. Appreciate it if you could mute yourself. Okay. So I guess DERs, as you just saw in one of the examples, are the cornerstone of microgrid systems, and we'll be talking more about that. But before getting to that, let's just zoom out to grid modernization plan and what it entails. This represents a complex multi-objective problem that usually introduces more than one solution. Grid modernization can include many things, but these are some of the most common objectives that various stakeholders in power industry, including utilities and power consumers, have when they consider improving their systems. A hybrid solution that addresses a large portion of this objective is very likely to include microgrids and DER integration, distribution automation, grid level control monitoring and optimization, among several other things. Many utilities focusing on AMI. But today we focus on DER and microgrid integration solutions and leave the other venues for future works. Now that we know about what our objectives are and the solution for it, how we can find the right location for our projects, which market is most suitable for our project, and what catalyst would impact our project's success. So these are all the questions the developers and the project owners would ask. One of the strongest drivers for microgrid application has traditionally been the high cost of delivering power, either attributed to the electricity price or the need for upgrade in grid infrastructure. Next in the list is usually the desire for higher reliability of the service. Another one that we see an increasing interest for it is monetizing the grid services. Just imagine energy storage that wants to participate in ancillary service market as frequency response in other ancillary services, as an example. So looking for policies and regulatory benefits and available technologies also can be considered to determine the optimum location and type of the microgrid projects. Now, let's take a closer look at what the process of integrating a microgrid, and in this case actually is DER into the system would look like. And let me just also set the ground rule for our presentation today. Unless that we specifically mention an application is applicable to either just DER or microgrid, for the most part, the contents in presentation today would be applicable to both. We'll see later on in the presentation there will be some specific application just for microgrid, which to us is a more advanced application of the DER in the system. So now here, this is one example of a type of analysis that the utility would do when they just consider integrating DER into the system, or even sometime before that, we had utilities approaching us and just want to be in front of the game, and knowing that as they have increasing interest for DER integration into their system, at which point in the future there potentially may be adverse impact into their system, and there will be challenges into their system. So that's what we are doing. This study is called DER hosting capacity, and what it basically it does is that when a utility receives a request for DER installation and how much DER can be hosted by each given feeder, they tend to perform this analysis. So at that point, they know that what is the capacity for each distribution feeder before the system really be technically challenged. So the objective of the study, as I said, is to determine the maximum amount of the DER that each distribution feeder can host. There are technical threshold, mostly voltage limits, and also the thermal opacity of the feeders that are usually being closely monitored to see that at which point those will be exceeded. The study applies either a probabilistic or deterministic approach, meaning that if there is some unknown in the system as far as the size of the DERs or the location in the system, then we can run some sort of a stochastic scenario, which means that it's a scenario-based, a Monte Carlo-based. There are different approaches for such analysis, or it could be deterministic in a sense that the utility knows exactly where those DERs are going to place based on the request that they received. The example shown here is from a study we performed for a utility in the US. And this example feeder, the probabilistic approach, keeps adding photovoltaic generation sources at different sizes and locations into the system and keeps evaluating the voltage profile across the feeder. In this example, this designated feeder can accommodate up to 500 kilowatts of the PV without any voltage problems, and even up to just about 1100 kilowatts at certain locations. So similar study will also be performed for evaluating thermal limits of the equipment on this feeder as well. This study specifically was done using the software named Synergy, but there are other commercial software tool, SIME-DIST, SynCal, Siemens SynCal, among a few others can also have be used for performing this analysis. So my apology for text-heavy slide. This is the only one I have here, but just wanted you, without going through all the details, for you to have an idea about some key categories of analytical studies that need to be performed as part of the design and implementation of the DERs and microgrids. It usually starts with what we call techno-economic feasibility study. And the objective is to determine the high-level conceptual design of the system, followed by a series of more detailed studies to determine the final design of the system. We just talk a little more about the microgrid feasibility study, which usually include technical and financial considerations to determine the optimal size of generation sources, developing functional description for microgrid operation, and preparing conceptual design. Here I wanted to show you a sample report for a techno-economic feasibility study. This one was for a project that used PV plus battery storage system. On the left, you see a simplified schematic of a project model in its software named Homer. And this one specifically is Homer Pro, which is being widely used in industry for feasibility studies among several other softwares. What this analysis do is to calculate the expected PV production for planning horizon and to determine the proper size of the battery storage to capture the surplus of the PV generation, as well as providing demand charge reduction. The output of this study would also include financial metrics, including net present cost. It's shown, it's pretty, dense. The result you can say about somewhere in the middle. You can see on the top perhaps the NPC, the levelized cost of energy, payback period of the project, among a few others. Again, it's just like it give you an idea about what we are looking here when we say techno-economic studies, as the name suggests, at the high level financial, high level technical. And then these parameters can be compared between various options to determine the optimal solution for any given project. But why we need microgrids? Beside load centers, there are three distinct components in a microgrid, including switching equipment, controls, and DERs. Each of those offer advantages that can benefit the end user and improve the performance of the system. According to Microgrid Knowledge Group, the microgrid is defined with 3 key characteristics. It's local, meaning it creates energy for nearby customers. It's independent, meaning that it can disconnect from the central grid and operate in an island mode. And also it is intelligent, which mainly refers to application of the microgrid controller. In this example, we are showing a use case that there's a fault in the distribution system, and the microgrid protection would detect that, and the control manages the local DERs within the boundary of the microgrid, such that the microgrid would disconnect from the grid and form an island. When the fault is clear, the control system would again communicate with the DERs and to adjust their power outputs such that the system can securely connect back to the grid. So that's just like one benefit, but you can think about improved reliability and resiliency. And as you can see in this example, you have renewable energy and a lot of others. We can talk a little more about that, about the benefits coming out of applying this microgrid in the system. One salient feature of the distinguished microgrids so far, you can tell, is from large, as opposed to large power generation centers, is in fact that they can include variety of generation types, including renewables, energy storage, and any conventional generators, as you just saw in a couple of examples presented so far. In the next couple of slides, I'd like to briefly discuss the considerations that need to be made in when you made the DER selection into the system. So these are there are several considerations that need to be made for applying DER technologies, but these are some. I guess I do not see the entire slide on my side. It could be just a. Let me see if I can just zoom out. Yeah, for some reason it's just not showing this part of this slide, or actually, oh no, I see that. I'm sorry, it does have animation and I didn't get that. So anyhow, so these are the 3 main features that we want to, or considerations that we want to look for when we are selecting DERs into the system. So the first one is power and energy capabilities. Some DERs may have large power capacities, but may not necessarily be able to put that power out very quickly. In a reverse situation, a DER may have a large energy content, but not a lot of power capacity. And the second feature is the response time to the system event. And by system event, I mean any changes in the current state of operation in the system, like changing the load or occurrence of the fault. For example, inverter-based sources have significantly faster response time since they do not have the inertia that the reciprocating machines have. Last one is one of the very important one because paralleling and interconnection limitation needs to be considered as part of the DER selection, since the system needs to function through different use cases, where DERs may need to be able to connect or disconnect from the grid when they control commands. We published a paper on the subjects for SIGRE a couple of years back that I assume it's publicly available, that you can just read through that. We also presented a webinar just on this topic. So there's a lot of content and considerations need to be made, but I'll leave you to go through that if you're more interested on these subjects specifically. Just this a little more on a tabular format. I want to show you, what goes through the mind of an engineer and developer when they're thinking about different DERs in the system. as this is the most important part of any techno-economic feasibility studies. At the end, one that one would immediately look for in the study report would be the size and type of the DERs for any given project. For example, if a project objective is to reduce carbon emission, then renewable sources need to be included. However, such clean energy comes at the cost of reduced flexibility because it really depends on wind or solar irradiance, and it's not dispatchable. So this can be offset by energy storage application, but then these resources are also usually very expensive. So the final generation portfolio may likely include gas or diesel generators too. So I guess here you can just put the paper titles for you also if you just want to search for it and read more about this subject. So yeah, I guess at this point I would just pass this to my colleague Michael Higginson, so he can talk more in details about some of the challenges we discussed earlier. And with that, Michael, please take it from here.
Thank you, Saeed. So while Ash is going to go here and transition our presenters over, so I'll share my screen here shortly. And it looks like this is coming across. Ash, can you confirm this is?
Yep, all good.
Wonderful. So thank you, Saeed, for setting the stage here. As we introduced, distributed energy resources are increasingly becoming more and more significant part of the power system that we're working in, and the transition to distributed resources represents one of the most significant transitions since the invention of the power systems. There are many challenges associated with integrating these distributed energy resources with our power system, and I'm going to focus on 3 of them today. Those 3 are protection, control, and stability. Of course, these are not exhaustive. There are many more factors, but these are 3 key factors that we'll highlight today. The first we're going to touch on is protection. How does power system protection change, and what are the challenges when we integrate distributed resources into the power system here? One of the most significant things to consider is the changing way that fault current is produced. Many of our distributed energy resources are inverter-based resources. That means they're interfaced to the power system through an inverter. Some examples can include solar photovoltaic system or PV systems, battery energy storage systems, and many modern wind turbines, which are interfaced to the power system through inverters. The behavior of inverter interfaced resources can present challenges to protection. And it's foundational to understand here why are inverter-based resources different. There are 4 main aspects here that I want to highlight. First is fault current magnitude. In all of these, we will contrast between inverter-based resources and conventional rotating machines. Inverter-based resources typically have fault current magnitudes that are comparable to their maximum load current levels. This can be on the order of between 1 and 2 per unit current maximum is typical for an inverter to contribute to a fault. This is substantially less than rotating machines, which can typically produce 4 to 6 per unit current when supplying a fault. This fault current magnitude is lower from inverter-based resources because the power electronics need to be rated higher to support more fault currents, which adds to the cost of resources, and generally that is kept close to the inverter rating to efficiently design these resources. Another thing that's significant here is fault current angle. With conventional sources, we could assess the magnitude and angle of the fault current by considering a Thevenin equivalent source, where we have a voltage source behind an impedance, and the impedance of our rotating machine plus the impedance of the system between the machine and the fault would drive both the magnitude and angle of the fault current contributed. With inverter-based resources, this can be different. The angle of the fault currents can often be driven by the control mechanisms and control algorithms that are present in the inverter, which can drive significantly different angular responses and magnitude responses to faults depending on the settings configuration of an individual inverter, as well as the controls that were programmed into it by its manufacturer. Another major factor to consider is response time. As Saeed mentioned, inverters are very fast switching devices and have the capability to respond to events quite rapidly. However, in many cases, especially when we're using grid following inverters, they are monitoring system conditions and adjusting magnitude and angle of current output based on what they're measuring over a period of power system cycles. That contrasts with the fault response of rotating machines, which is driven by the physics of the machine and will happen instantly upon fault inception. The physics plays out the fault response. Another key characteristic is negative sequence current. Negative sequence current is present in unbalanced faults, and it is something that we very commonly use in our protective devices to identify the presence of a fault, as well as identify the location of that fault. Conventional rotating machines, of course, produce negative sequence current in response to unbalanced faults, like a phase to earth fault or a phase to phase fault. Inverter-based resources, the negative sequence current can vary substantially. Many inverters are programmed to intentionally suppress or reduce the negative sequence current output, especially in grid following applications. This can challenge existing protection schemes. Furthermore, the magnitude and angle of the negative sequence current can be significantly impacted by the controls of the inverter, which again will vary from the Thevenin equivalence-based and impedance-based negative sequence response of a rotating machine. So you can see several of these factors are quite different and unique when we integrate inverters and consider how they will contribute to faults, especially as they are displacing existing conventional rotating machines. They'll drive on net a reduced fault current throughout the power system. One way I often like to represent this is looking at microgrid applications. As Saeed mentioned, microgrids can operate in either grid-tied or islanded configurations. They can operate in parallel with the bulk system or separated from it. And the fault currents that you can see in a microgrid can vary substantially between these cases. This plot I show is from an actual project that I've worked on in the past. And you can see very clearly here, in grid-tied situations, the fault current shown at the gray bar on top substantially exceeds the load current shown in the green bar on the bottom. This is useful, and this aspect or characteristic of systems is something that we leverage in setting our protected device settings. We often are protecting our distribution systems with overcurrent protection, and this looks for currents to be higher levels. in grid-tied applications, it's very clear that overcurrent is a useful tool to be able to detect these events. If you look over at the plot on the right, or the part of the plot on the right, you can see that fault current levels and load current levels are overlapping. The fault current can vary significantly based on what resources are online and supplying the load at any given time when we're separated from the bulk system. And in some cases, with low amounts of generation online, the fault current can be less than the load currents when higher amounts of generation are online. This can obviously challenge the use of overcurrent protection and make it impractical to use solely overcurrent protection in microgrid applications. Another challenge that we face when we're integrating distributed energy resources relates to where these resources are located. Distributed energy resources are pervasive and throughout the system, which can result in bidirectional fault current. And to really illustrate this, I think it's best to look at an example system. This is an example simplified system one-line diagram based on a system that I've spent significant amount of time working on in the past. First, let's walk through the single line diagram here. Over on the left, we have a substation with 3 reclosers as protected devices and the main bulk power system source coming in at the top. This connects to loads over on the right, and on the left, there are also some loads as well as microgrid switchgear, which interconnects a variety of different distributed energy resources. Now, in this system, let's look at what happens with faults at different locations. If we have a fault over near the generators on the far right, you can see that fault current is coming into the switchgear on the left and out of the switchgear on the right. Now, if the fault was instead on the tie line between the substation and the microgrid switchgear, we see fault current coming out of the switchgear on the left and in on the right, the exact opposite of what we just saw a moment ago. Now, clearly, the protective devices that respond are different in each of these situations, but we're seeing fault current in both. So it becomes essential and very valuable to detect direction of fault current in microgrids and change protective device behavior as a function of the direction that we're measuring fault current flowing in to ensure we have a selective, coordinated protective response where the right protective devices are operating to minimize the extent of outage. System protection also needs to consider the system dynamics. And system dynamics can be significantly varying during microgrid islanded operation. When we have a small amount of generation online, when the system load changes, frequency and voltage can vary as a response. And this frequency and voltage variation in response to the load change should not cause the protection to trip. This would be undesirable and result in load being disconnected and customers outaged. Alternatively, during system faults, the voltage will be severely depressed and the frequency will vary significantly, which the protection must trip quickly during to maintain stability. The system dynamics when we're islanded, the frequency moves and the voltage moves a lot more than when we're grid tied. So the same voltage and frequency protection settings that may work great when we're grid tied may be challenging and not work effectively when we're islanded. Another challenge that we face in microgrid protection is simply measuring current. As we highlighted earlier, in microgrids and in DER penetrated systems, fault current levels can vary significantly. Faults contributed to by local generation, especially inverter based generation, can have quite much lower magnitudes than our normal grid-tied fault current magnitudes. And to detect these, we need to select our current measuring tools consciously and effectively. Current transformers are the most common tool we use to measure current. And to select them appropriately for a microgrid application, we first typically look at the ratio, and we try to identify a current transformer ratio that will enable our protective relays to detect the lowest levels of fault currents that we are facing or expecting in this system. Now, the challenge that goes with that is if we reduce the ratio, our current transformers can be driven into saturation with the high grid supplied fault current levels. And the current transformers are a static resource. They're not going to change when we change between grid tied and islanded mode. So we need to select them to work across both. Over on the right, you can see selecting current transformers, which are shown right here, that work for a microgrid application can result in having quite large, physically large current transformers, because we need a high class to a large amount of iron to avoid saturation with the low ratios we need to detect the current. These current transformers you see in the image are quite large. In fact, the current transformer for each phase in this switchgear weighed over 50 kilograms. So these were physically quite large current transformers. Now, there are other tools that can also be used to measure current. One of those is Rogowski coils. Rogowski coils can be linear across a wide range of current application and can enable accurate current measurements from single-digit amps up to tens of thousands of amps. This is very effective for microgrid applications. And fortunately, some commercial products enable the use of Rogowski coils with protected devices. One of those is a product that my employer makes, the S&C's interrupter pulse closer, is a protected device that uses Rogowski coils and can enable detecting both low and high fault current levels accurately. Another technique and approach that we can use to protect DER penetrated and microgrid systems is adaptive relaying. There are many different forms of adaptive relaying. The two major forms are either pre-selected settings groups or on-the-fly adjusted protection settings. My personal preference is towards pre-calculated settings groups that we have defined and our confidence will protect the system through the modes of operation we're expecting. This can be easily identified in microgrid systems where we have a significant difference between grid-tied and islanded behavior. We use this in tandem with custom fault detection logic as well to ensure that we're detecting faults both accurately, sensitively, and securely and reliably. Now, how can we change the settings? What kind of things are we looking to change? One of them is overcurrent. When we're grid tied, we can have less sensitive settings to detect the high fault current. While we're islanded, we may want to make it more aggressive and be more sensitive. You might ask, why not just make it more sensitive all the time? Well, when we're grid tied, we could have transformer magnetizing inrush or large block loads or other conditions that could cause the current to elevate, and we don't want to cause nuisance tripping or nuisance operations. Over under voltage and over under frequency are also other settings that often change between grid tied and islanded modes. When we're grid tied, the system is stiffer and those settings can be more sensitive. When we're islanded, those settings must be a little looser to allow for system dynamics when we're accepting load, and typically are less sensitive, allow for a little bit more normal variation. Reclosing is yet another thing that changes between modes of operation. When we're grid tied, reclosing is an extremely valuable technique to improve system reliability and address temporary faults, ensure that temporary faults aren't causing permanent outages to customers. When we're islanded, reclosing can be very stressful on the weak system with limited generation. So we often limit the reclosing that we're using when we're islanded. Some forms, such as pulse closing, which the interrupter pulse closer does, is less stressful on the system and, depending on your application, may be acceptable when islanded. Now, if we're looking at different settings groups or changing our settings to protect the system, there's a significant question that arises here. When are we going to switch between our settings groups, or when are we going to adjust the settings? Because if you're adjusting the settings, your protected device may be in an indeterminate state for some time while it's making those changes. And we want to ensure we're making that in an intelligent way to ensure the system is protected at all times. Again, this is well illustrated with a microgrid example. And again, I'm showing the same system that I've worked on in the past. This uses a distributed control architecture with several relays shown with the R label here for relay. We have controllers shown with these gray boxes located at several different locations. Now, one approach that we've used to success in several past microgrids is a staggered approach where we change some protective settings immediately prior to making a transition from grid tied to islanded or from islanded to grid tied. And then we change the remaining settings as soon as that transition occurs. This staggered approach ensures that the system is protected throughout the transition, which is a key critical time for the microgrid. Now, this particular approach that I'm describing is something that we've applied for and successfully patented in the United States. Another approach or technique that's quite useful in microgrid and distributed energy resource integrated systems is directional interlocking schemes. These schemes will involve relays measuring directionality of the current, as I described earlier. And the relays can communicate with one another. A typical way that we've used is IEC 161-850 Goose messaging. And Goose is particularly useful for two major reasons. One is because of the publish subscribe model. It enables one device to communicate with many other devices straightforwardly, which is useful in complex system topologies that microgrids often include, and DER penetrated systems often include. Additionally, Goose messaging is a quite fast protocol. We've very commonly achieved less than 4 milliseconds round-trip communication time, where one device sends a message to another and receives a response acknowledging that message in less than 4 milliseconds, which is quite fast. This goes through Ethernet switches and through media converters and still can be quite fast here. This directional signal communicated via Goose can be sent to all neighboring relays, which can then use that signal to decide whether it's appropriate to trip, whether it's appropriate to block, to transfer trip, or to lock out in some situations. This figure, again, is a great way to show an example of how exactly this would work. Let's consider an example fault over on the far right by the generators here. In this situation, we'll see current coming out of the switchgear on this far right, through this far right circuit breaker. And the relay associated with this device can send a blocking signal to each of its neighbors here so that they restrain operation and allow the device closest to the fault to operate first. Similarly, the switchgear breaker and its associated relay can send a goose message up, blocking its first upstream device, which is at the substation, and telling it to hold off until downstream protection operates, and so on. And this scheme can result in the correct device operating very quickly while maintaining selectivity and ensuring the correct device is operating. Now, fortunately, microgrids and DER integration are a topic of a lot of ongoing industry work here. And there are several resources available to you. Some of the examples that I described, or all of the examples I described, have references to industry work here. IEEE PES Technical Report 71 is out as of mid-July 2019. This is a resource that I chaired the development of, and it talks about a lot of the topics that I've covered over the last 20 minutes here. We're working on a guide for the design of microgrid protection systems as well. I'm also leading that working group. And Seagray also has several documents that are relating to distributed energy resource integration protection, including working group C6, some technical brochures, as well as some other PSRC reports and industry papers. There's quite a bit of work out there that you can reference for additional industry guidance on microgrid and DER integrated protection, with more being developed as we speak. We just talked about how protection can be challenged with integrating DERs. Another topic that is DERs introduce new challenges is in system control. I like to start talking about DER integrated system control with a hierarchical approach, because hierarchical approaches are very effective in managing the power system's needs and ensuring they're met with distributed energy resources in both microgrid and modern distribution systems with DERs. At the lowest level, we have device level controls. We call this the primary level quite commonly. These device level controls include the inverter local controls, which will decide how to gate the inverter and switch it to produce a commanded amount of power at any given time. It also includes generator governors and exciters, and protective devices also fall into this primary control. These are devices that are using local measurements to make decisions primarily, and can make these decisions on the order of microseconds or milliseconds. Sitting above that, we have a system level control or secondary control. This typically operates on the scale of hundreds of milliseconds or seconds. The system level control typically will communicate with device level controls that are downstream of it and ensure it understands the status of all these device level control, or the devices that are controlled at the primary level, as well as issuing commands to ensure that primary level devices are operating appropriately for the system needs at any given time. Sitting above the secondary level is the tertiary control, which is typically responsible for slower considerations like economic dispatch, things that operate on the scale of minutes to decide what resources most cost effective to operate at a given time. Like I said, this hierarchical approach can be applied to both DER penetrated systems as well as microgrid systems. Let's look at what's entailed in some of those different examples here. In grid-tied systems, we have our controls will be responsible for aggregating resources to ensure we can effectively control the multitude of devices out on the system. Our controls will manage the voltage and reactive power, which can, as you may know, voltage profiles change quite significantly with DER penetration, and it's important with increasing DER penetrations. It's more and more important to ensure that the voltage is controlled to maintain power quality to customers throughout the system. In some cases, curtailment may be needed to meet system needs, and a controller can manage those, deciding what devices should be curtailed and to what level. We can provide grid services as well with our grid level controls. We can dispatch the primary controls to respond appropriately to system events or meet system needs in the event of contingencies, or to ensure economic operation. IEEE 2030.11 is a good reference that describes many of the grid tied control needs in DER penetrated systems. At the opposite extreme, we have standalone systems, which are never interconnected to the grid. Standalone systems focus on maintaining system steady state needs, ensuring that we have enough generation online to meet both the present system needs as well as impending expected system changes. In the middle, we have microgrids, which are capable of both operating standalone and operating grid tied. And it really utilizes use cases from both grid tied operation as well as standalone operation. With a microgrid, you need to cover both use cases. Now, because of that, microgrid controllers, or controllers that are applicable and usable in microgrids, can often be applied to standalone systems. In microgrid systems, we also, in addition to everything that's listed in grid tied and standalone, also we need to manage the transitions between these grid tied and islanded modes of operation to ensure that the transitions are orchestrated effectively. IEEE 2030.7 is a great reference describing the microgrid control system needs, which also, of course, encompasses standalone power system control needs in many cases. One of the challenges we consistently face especially in islanded systems, both standalone and microgrids that are operating islanded presently, is ensuring that load is met. What I mean by this is we take it for granted that when we flip a light switch, that the power is going to be available to, and the system will adapt to this change. But somewhere a generator is ramping up or down when you turn on or off, respectively, a light switch or any other load. Someone needs to supply that power. Now, this can be particularly impactful in microgrid or islanded systems where we have a very limited amount of generating resources. And small changes in load, not as small as a light switch, but more significant changes in load can have an impact on the system dynamics. We need to think carefully about when load turns on, what resource is going to adjust its output to accommodate this changing load. And there are two major ways that we do this. One is with isochronous. Yes, hello? Okay, not sure what that was, but moving along, there are two different ways that we handle these load changes, and both of them are with grid forming resources. Grid forming resources attempt to maintain voltage and frequency output as opposed to maintaining a constant power. One of those grid forming approaches is isochronous. Isochronous controls try to maintain a constant frequency and a constant voltage across various load levels. If we have multiple isochronous resources, then you might ask, how do we identify which one is going to take on the additional load? And typically this is managed using load sharing algorithms that communicate rapidly between governors, exciters of resources from similar manufacturers to ensure that load is shared appropriately. When we have heterogeneous systems that utilize different types of resources or resources from different manufacturers, droop is a technique that we commonly use. And droop is very similar to isochronous, except for we adjust the voltage and frequency as a function of the power output to share load between resources. And I'll expand upon that in just a moment on the next slide. Grid forming resources are operating in isochronous or droop typically, and those resources are commonly generators or battery energy storage systems. We need capacity resources that you can count on to adjust their power output and have power available if more or less is needed from the system. On the far right, you see commanded power output or curtailment. This is the mode we most commonly operate in if we have a grid following resource. Think our rooftop solar or wind and solar resources are typically grid following and not grid forming. Grid following resources require that grid forming resources are present. Some resources have to maintain voltage and frequency. We need at least one that's grid forming. Our grid following resources just output as much power as they have available or operate at a specified power output. We can have some voltage and frequency support functions, but typically this is operating at a slower speed than our grid forming resources. Let's talk a little bit about droop. Droop is one of my favorite load sharing methods because it works across manufacturers and across a heterogeneous resource pool. This is something that I've used quite frequently in systems that I've worked on in the past. The graph over on the right shows what droop curves can look like here. I showed 3, and this shows it. This is for an example microgrid system. In general, you see on the y-axis the system frequency in hertz. And this is based on a 60 hertz North American system. And on the y-axis or on the x-axis, you have power in kilowatts here. You can see that in general, with frequency increasing, the power output decreases, or with a battery system, power is absorbed. And with a decreasing frequency, power output increases up to the maximum that the resource can produce in both batteries and generators. You can combine the separate droop curves from a battery system, generator system, a variety of systems operating in droop to also get a system effective response, which shows you what the system frequency will be operating at across a range of power outputs. One other technique and useful approach that I want to talk about is seamless unplanned islanding. Seamless unplanned islanding involves components of both control and protection that we've talked about here. Of course, when there is a fault or a loss of source on the power system, we need to ensure that we're disconnecting our resources to ensure that the fault gets de-energized and to ensure that crews can safely isolate and operate a system. If we need to disconnect our resources, and that is a permanent outage, the resources, our DERs also need to be available to supply an islanded system. How do we balance those needs to both disconnect and de-energize a fault, but also keep our DERs available to energize an islanded microgrid system? Seamless unplanned islanding is an approach here. What this does is, instead of disconnecting individual DERs for a system fault, is we will disconnect the entire islanded microgrid system to separate all of the DERs simultaneously from the system fault but also keep those DERs online and available to supply the islanded microgrid system. This involves a combination of a higher level controller, which is monitoring system status and ensuring that the resources are always dispatched such that they can support the microgrid if an islanding situation came up, and fast protective devices that are detecting an event very quickly and operating. This is an approach that we've used successfully in the past. You can see some oscillography. This is from an actual event at one of the microgrids that I contributed to the design of and commissioning of. On the top, you see fault current here, and you can see there's very clearly a fault occurring on the power system right around this dashed red line. The fault persists for about 100 milliseconds, and then it's clear. And you see a lot more here down on the voltage plot on the bottom. You can see at fault inception, the voltage starts collapsing and retains at a collapsed level throughout the fault. And you can see just one line over on the left. But right here, there's a red line that separates from the green lines. This is showing that the system voltage winds up collapsing after we separate, while the islanded system actually recovers. In this event, the local customers didn't even know that a fault occurred. The lights may have dimmed for a brief moment, but we recover seamlessly to an unplanned islanding condition where the DERs have disconnected to de-energize the fault, but also maintained islanded operation. The last challenge here that I want to highlight is stability. There are 5 major impacts that DERs have on the bulk system when we're integrating these resources. They are on voltage control, frequency control, short circuit levels, control interactions, and power system modeling. Let's talk about each of those individually. With inverters displacing rotating machines, there's a need to maintain the voltage control for the bulk system that rotating machines have traditionally supplied. This requires reactive power support. Legacy inverters in particular often were designed to maintain only unity power factor at peak active power output, because this is a cost-effective design to supply power and focus on active power, which is typically compensated by markets, over reactive power, which is often not compensated by markets. It's important as inverters displace rotating machines that we have reactive capability in our inverters to supply the reactive power needs of our power system and ensure that we're meeting the system needs here. It's also important that that reactive power support comes very rapidly. When there's a system event, reactive power needs to be supplied very rapidly to maintain system voltage, which plays into the last point here. It's important that resources are capable of continued output at reduced voltage. As inverter-based resources become a more significant part of our power system and our bulk supply, it's important that they ride through events and continue to support the system throughout the challenges that the system may face. This includes reduced voltage during system faults. It's more important than ever that DERs ride through and continue to support the system as the voltage is depressed to maintain system stability and ensure we can recover. Frequency response is also key here. There's a reduction in system inertia as inverter-based resources displace rotating machines. Rotating machines have a large rotating mass that helps provide inertia to bulk power systems. This rotating mass can help correct for mismatches between prime mover supplied power and instantaneous demand. If you take it at a very small scale, think again of switching the light switch on and off. A generator needs to ramp up or down to change power output for the load change that we're making. If we have a large rotating mass with a rotating generator, we can take some power out of that inertial mass by reducing the frequency and getting some power out to supply that instantaneously increased load. Or vice versa. We can speed up the rotating mass in the short term to account for a decrease in load that we're oversupplying. With rotating machines being displaced by inverter-based resources, we have a reduction in system inertia. We have less rotating mass to compensate and absorb these changes, which results in faster changes in frequency when we have a system event. Consequently, it's imperative that our resources respond very rapidly to frequency changes in a low inertia system that we expect with highly penetrated DER systems, as well as inverter supplied microgrids, or microgrids in general are typically low inertia. One of the challenges here is maintaining or supplying additional power output when it's needed. A common event we consider on bulk systems is the loss of a large generator. If we lose a large generator, the remaining resources need to ramp up power output to meet the deficit in supply that is realized when we lose a generator. Now, this can be challenging with inverter-based resources because many of them are dispatched at the maximum power output available from the fundamental resource. For example, solar farms typically output as much power as they can given the solar irradiation. Wind farms typically output as much power as they can given the wind available. If that's how a system is operating, when additional power is needed, the resources don't have additional power to provide. We can address this through curtailment or consistently operating our resources below the maximum amount of power available, but this is counter to the economic incentives. We're financially incentivized to run the resources at the maximum they can output. But as these resources, as inverter-based resources and renewable resources become a more significant component of the system, it's critical that we maintain some level of reserve or have some other mechanism to ensure, such as energy storage or synchronous condensers or other approaches, to ensure that we have power available to compensate for deficits when we lose resources. Similar to the low voltage situations, it's imperative that our inverter-based resources and our distributed resources ride through frequency events as they become a more significant component to ensure that they can maintain system power needs. The last three stability concerns I think really go together, and I want to interlink. Those three concerns are system short circuit levels, control interactions between devices, and how we're modeling the power system. As we've discussed to a significant extent already, displacing rotating machines can reduce the system short circuit levels. This impacts our protection, but it also impacts system stability. Reduced system short circuit levels can be a challenge for inverter-based resources themselves, which often require a stiff system for their control loops to work properly. The reduced short circuit levels can also exacerbate voltage sags that we experience during events. We can have deeper voltage sags in a weaker system. As we talked about in the protection section, inverter-based resource short circuit behavior can vary significantly, and the way we've traditionally modeled power systems has to be adapted to account for these different behaviors in inverter-based resources and how they're acting during system dynamics and system short circuits. And finally, we have increasing penetrations of power electronics with these inverter-based resources, which introduces more and more opportunities for the power electronic controls to interact with one another, which is something we must ensure that we're looking for in our models as well as our system operations to ensure we maintain stable operation and are cognizant of possible control interactions between resources. So we just wrapped up 3 major challenges that we face with increasing DER penetrations, including in microgrid systems. These can include protection challenges, control challenges, and power system stability challenges. We started with an introduction to grid modernization and how these distributed energy resources are becoming a more and more pervasive part of the power system we work on and rely on for our electricity. We talked about how these resources, how selecting these resources can play a significant impact in the behavior of the system and some of the challenges of integrating distributed energy resources. Well, let's wrap up here with a couple key takeaways. One takeaway that I want you to walk away with is both microgrid protection as well as broader system challenges have significant ongoing industry attention. There are several published industry standards, which are great references on many of the topics we talked about today. And there's continuing ongoing system work that is working to address these challenges and provide guidance to power system engineers on how to properly and successfully integrate distributed energy resources as they become more and more pervasive in the power system. In conclusion, if you could only take away a few things here, what we hope you take away is that integrating distributed energy resources is inevitable, and this is where the power system is going. But this integration brings new challenges throughout the power system. Addressing these challenges requires coordination of many components, including our distribution automation systems, our inverters, our controls, and our system modeling, as well as many other components. These need to be coordinated to effectively operate our resources in a distributed energy resource heavy system. We also need coordination of different disciplines. Different engineers who handle different aspects of the power system need to ensure they're coordinating as many of these topics become interlinked and introduce new challenges with inverter-based resources. And finally, integrating DERs is part of grid modernization. And grid modernization includes many other aspects, like ensuring we have reliable distribution systems where these DERs are interconnected. It's important that we have a coherent and comprehensive solution to address these challenges and ensure we have a effective plan for where our power system is going. With that, that's all I have for today. Thank you all for joining. We appreciate your time and attention. We hope this has been an engaging topic for you. And both Saeed and myself would be happy to discuss any items both in the Q&A now. Feel free to reach out with questions you have now, as well as if you think of something later, we're happy to address them. Feel free to reach out via the email addresses I share here. I saw a few questions coming through in the chat, but haven't been following them. Matthew, can you introduce some of the questions that our viewers and listeners have today?
Yeah, definitely, Michael, and I guess thanks again, very interesting presentation. I will run through the presentation in the the questions I should say, in the rough order that they were received. So we have a question from Saeed, and it seems to be a fairly general one. Just looking at what about some of the considerations with zero sequence current from inverter-based resources? Is that, I guess, an issue for microgrids or something that you've looked into, I guess, compared to synchronous generator performance?
Yeah, this is a great question, and thanks for raising this. So both negative sequence and zero sequence contributions are, of course, important. But I only really touched on negative sequence in the presentation. So it's great that you're bringing up zero sequence, which is also important. Zero sequence is a little bit more straightforward to address. System grounding is, of course, a challenge that is interlinked with zero sequence networks here, how we interconnect our resources. The reason I didn't spend a lot of time on zero sequence currents is because this is something that we can address with transformers. Positive and negative sequence current both require active resources that are supplying power, generating power to meet both positive and negative sequence, with the possibility of course, StatComs may also be able to supply negative sequence, but you need active resources to supply those, which is why I focused on it. Zero sequence essentially is power coming in on one phase and out on the other two, or in on two and out on the other one. And this can be achieved with transformers. So the two types of transformers most commonly used are zigzag transformers or Y-grounded delta transformers. And depending on where you are in the world or the preferences of the system designer, both can do the job with, of course, different pros and cons for each. But interconnecting our DERs through a step-up transformer that has a zero sequence network that will supply zero sequence current can be one approach here where we need it, or having a shunt zero sequence supplying a grounding transformer, a shunt transformer that supplies this. That in and of itself is a complex topic, and I touched on the initial considerations. There's a lot more to that, and I'd be happy to discuss further, but I don't think we have time to go into more of the intricacies. I hope that satisfies that question.
I think that does. I mean, like you say, to the level that we can probably do without having a whole nother hour presentation. Thank you for that. So I have another question from Daiju that is looking at how often or under what conditions would you recommend running microgrids in island mode as opposed to grid tied? I mean, do you imagine the fault conditions that you sort of presented about is obviously one reason for that seamless transition, but are there any other scenarios that you would look at transitioning to island mode other than faults?
Yeah, that's a great question. In my experience, customers typically look at transitioning to islanded operation either in response to a fault or in anticipation of a possible event. For example, if we expect a storm to be rolling through and see a higher probability of outage to a certain part of the circuit, and it has a microgrid available, we might want to island it to ensure that, or to minimize the chances that the power goes out in that system, or that it's impacted by an outage at a different part of the system. Typically, economic considerations, it's typically economically advantageous to be grid tied. Usually grid tied power is cost effective, and many of the ways we pay for microgrid DERs are through grid services or interaction with the grid. So typically the only reason that I see that a system goes into islanded operation is either in anticipation of or in response to a system event. Great question.
Thank you very much for that. I might just check. I've got a question for Saeed, but I do believe we might have some connection issues with him. Saeed, are you online?
I think he told me that he might need to step away. I can try to field the question. I think I probably can address it.
Yeah. So the question was around the economics and sort of site selection and viability of microgrids that Saeed was talking to. I guess in the work that you guys have done to date, are you seeing microgrids as being a widely applicable technology or topology, or is it something that's sort of for that niche high resiliency requirement or high risk environment?
That's a fantastic question. They aren't pervasive, but they're definitely increasing in popularity. There are many microgrids. I think Microgrid Knowledge is a website that I'm not affiliated with, but I know does quite a bit of work with documenting existing microgrids, becoming more and more popular. We are seeing increased demand for microgrids. I wouldn't say they have risen to the level of being pervasive or ubiquitous. Not every utility has microgrids, has experience with microgrids, but more and more utilities are becoming interested or enabling microgrids in their system, as well as behind the meter customers that are looking to achieve renewable objectives or improve their resiliency or reliability through integration of resources. It's definitely becoming more common and more economically viable as markets increase in how they incentivize resources, as well as the cost of many of these resources continue to drop. Both batteries and solar photovoltaic systems continue to drop in price, which makes microgrids advantageous. Great question again.
Fantastic. We do have a couple more questions. We might. I had Maddie has messaged. I don't know whether you've received a question directly from Maddie in the chat, Michael.
Good point. Let me scroll around and see if I can find it.
If not, we've got another one. I'll give you a couple of seconds to have a look there.
I'm not seeing any direct questions that I received, unfortunately.
Okay. Maddie, if you're hearing this, if you can post that to everyone. Oh, here we go. So the question was, do you think inverter-based resources should also provide negative sequence current? And that with the context that Maddie sees some new grid codes coming out in this respect, asking inverters to provide this current during faults.
Yeah, I would echo the latter part of that. There's definitely grid codes and IEEE and other industry standards that are leaning towards requiring resources to be capable of supplying negative sequence current. Negative sequence current is essential for system operation, and as inverter-based resources become a more significant component of the total generation, it's more and more important that they carry their share of the unbalance in the system and are capable of supporting the system through unbalanced faults, et cetera. So I think it's very valuable, and it's something that can be important to enabling a more inverter-based resources to penetrate the system if they can support negative sequence current output.
Fantastic. And I think we have time for one final one before I hand it back over to Ash for the wrap up. So obviously a big part of your discussion, I think a very, very interesting topic as well, is around the protection performance or protection operation, moving to a world of microgrids and higher penetration inverter connected generation. So from that protection perspective, do you see the issue here being that inverters need to more closely mimic synchronous generators, or that we need to have a sort of step away in how we implement our protection systems and how it operates? I know you sort of alluded to the different ways of addressing this in your presentation, but I guess as more of an opinion or / technical perspective, what are your thoughts around that?
Yeah, I think that's a great question, and a very, very difficult question that I won't claim to have the right answer to, but I will give my opinion. As an engineer, when I see two extremes, like an either or, if there's a middle option, that's often the approach, and that's what I would say here too. I think there are certain aspects of rotating machines that need to be provided by inverter-based resources, or need to be supplied by some resource, and inverter-based resources seem like a good way to do that. If we're integrating the resource, might as well have them supply some of the system needs that they can. So the more we can help them integrate with the existing system, but then also the way we do things is going to need to shift. The way we protect the system needs to shift. So I think it's not one or, but both and. We're going to need to both adapt how our resources behave to ensure that we're keeping the system as effective as possible, as well as adapting our practices to meet the changing system needs.
Thank you very much, and thanks for taking the grilling on behalf of both yourself and Saeed. Yeah, some really good discussion. I do note that we haven't got through all of the questions, so if you do have any questions from Michael or Saeed, Ash has put their contact details back up on screen, and I'll hand it over to you, Ash.
Excellent. Thanks, Saeed and Michael, for that presentation, and Matt, of course, for moderating that Q&A. It was really insightful, and it's pleasing to see the level of engagement we generated. And yes, for any questions that we haven't answered, we'll attempt for Saeed and Michael to get back to you individually via email. So we've seen today how designing, implementing, and operating DERs and microgrid systems can introduce unique challenges and how we can overcome them. Just a final reminder to keep an eye out for future webinars on the NGN website. There's at least one more later this year. Bye everyone for now, and have a great day ahead.